the milestones we just mentioned. Okay. So far we have looked at endpoints. Let's say endpoints, or rather I should say we have looked at given endpoints. No, what is the most optimal way to connect them, right? Obviously this is a practically useful question, optimization question, and we also saw as mathematically an interesting question. What do I mean by connect them? Yeah, let us just quickly see that. Also, just give me 1 second. I think I have made a mistake. One minute. Yes. What's the most optimal way to connect them? Let me just also quickly describe what I mean by connect them. So, let's say we have 5 points. What do we mean by connecting these 5 points? We mean that we need to be able to draw enough edges, or we need to be able to join enough of them, enough of the points by lines, okay, such that I can reach from any point to the other. For example, this is certainly enough. Okay, so this is what I mean when I say connect endpoints. And this scenario, as we have said, that when you have endpoints and you have some number of points and you have some number of them joined to each other, some not joined, then this situation is called a graph. And if they are joined in a way that they are all connected, meaning you can go from any place to the other, then the term we use is connected graph. So those are just words. Okay. Now let's come down to um, sorry, just give me one more second. Right. And so what did we see here? We saw here that for endpoints, n minus 1 lines is the most optimal. Is the optimal. By optimal here we mean minimum, and we discussed how to get those n minus 1 lines. You can think about it if you don't remember it, so on. But this is what we got. And we saw that there are many ways to get these n minus 1 lines. Okay, but n minus 1 lines is the minimum requirement. You cannot do with less than that. So that's something that we proved. You cannot do with less than that. And also you can do with n minus 1 lines. Obviously you can just make a path, right? That's obviously one obvious way. But we also saw that there are many ways to get it. Okay. And so we saw as long as you make lines so that you don't make cycles, you will end up. So that gave us an algorithm and so on. And of course, we discussed some applications in Olympiad types and exam type questions. But let's come down to what we want to do today. Okay. So today we want to look at a collection of points which are joined by lines. So it's what you can call a network. Okay. But today we will look at a weighted graph. We look at uh, a weighted graph, but before that, let me just say look at an arbitrary connected graph. yeah, this is the first thing that we should do. This will be rather fast, but after that we'll do the weighted case. You see, we started with endpoints and then we just saw how to get the different types of connected graphs, the best connected graphs, the trees, we call them trees. But today we want to see that starting with a connected graph, so you can understand like it's some possibilities are given and we have to, from there we have to choose. Okay. So we will look at an arbitrary connected graph and see how to extract the minimum from there. How to extract, okay. See how to extract a minimum connected from it. Okay. Obviously, we'll also see how to do this algorithmically. I mean, mathematically, obviously, maybe it's already obvious that it's true. You can always extract, but we'll see mathematically. Or, sorry, we'll see algorithmically also how to actually perform it using some simple rules. Okay. But let's take an example first. Okay, so to make it clear. See, first of all, is it obvious that if I take, let's say, some points and I take a connected graph. So now we are taking some graph that is connected. Take a light color. So let's say, but this is not the optimal connected graph. It's just a connected graph which I'm drawing. Maybe just, or maybe one more we can draw like this. Okay. So you see, this is just a connected graph. Is it, so number one question is it optimal? No, right? It's not the optimal because, so can anybody just say why it's not optimal? Simple, simple question. Yes, that's right. There are cycles, and you can simply just think of removing some edges. You can remove this edge, and you will still have a connected graph. So this is not the optimal one, but it's a connected graph, and so that is what we are trying to understand. It's an arbitrary connected graph. Okay. How can we extract a tree from here? Now, what do I mean by extract a tree or extract a minimum connected graph? I mean that we want to create a minimum connected graph, but using only the roads, the edges, the lines, whatever that are available to us. Okay, so this means using only the available. So initially, we had a lot of freedom. We could just make a path, but now it's slightly more interesting. But we have already discussed the idea of this. So it will be easy using only the available edges. So first question is it possible? Is it possible in this case, or and then is it always possible? Can someone try to explain it? Yes, exactly. That's what I mean by extracting. Right. Right. That's correct. Right. So that's why you see the word extract is better than just saying that. I mean, if you are asked to build it from an empty graph and using only the edges that are available, that's obviously way it can be framed. But the easier way to do, as you have mentioned, is by removing some edges. Yes, and by removing. So can anybody go in more details as to how what edges should you remove and so on? Okay, can you repeat that? Can you say it more clearly? Yes, that's right. So you have to simply remove one edge from a cycle, okay, to start with, right? So remove some edges, so which belong to cycles, right? So that is what we have to do. So is it clear to everyone that this eventually will lead us to an optimal connected graph? What is the proof? So just to quickly do it in this case, I mean, so it looks very obvious, but to write a proof we have to still mention. But let's just look at it in this case. In this case, for example, you could remove the 4 3. So here maybe I just write it here, remove 4 3, this edge, and then see there are several choices, so one must understand this. And this is an important point. There are several choices. You could remove 4 3, you could remove 2 3, you could remove 2 4, but we are claiming that it doesn't matter, you can remove any one of them. So here it's fine. In the weighted case it will be that will feature and will get interesting. But here it is just removing 4 3, for example. So that's step one. And then in the next step, you can remove something from this cycle. And the key is that it will still be connected. If you remove an edge from a cycle, it will still be connected. I suppose everybody can see that, because if you have to write it, you should be able to write it. Okay. Obviously, we have seen that earlier. And then in the next step, again, you can remove either of 1 2, 2 4, or 1 4. So just remove 1 4, for example. In this case, it doesn't matter which one you remove, but yeah, later on it will matter. And that's when it will get interesting. But yeah, here we're just saying remove of 1 4. Simple. So in this case, we see that if you do it, you get a tree, right? In this particular case, this is a tree, right? Because it doesn't have any cycles, it is still connected. So it's clear. How do you write that in general? Okay. How to show that it will work? How to show that this will work in general? How do you explain that? So if you have n vertices and it's just connected, then and at each step you remove a edge which belong to some cycle, then you look at the remaining picture and you do the same from there. I mean, how do you show that this will eventually give you a tree, a minimum connected graph? Mhm. M edges. It's not a tree, it's just a connected graph. That's what we have to show. That's right. That's what we want to show. So we want to show that eventually we will have n minus 1 edges. Obviously, after that process that has been described is run, eventually, how is that What do you have to quote, or if you don't want to quote, it's even better. How do you explain that you will reach n minus 1 edges? Because the way we are doing it, it's not very clear that, I mean, it's maybe it depends, but it's a priori just a greedy algorithm in some sense, right? You're just trying to remove an edge. So you're just locally thinking of, reducing. Why will that globally give you a minimum? So, yeah. That's right. So that's the algorithm. But why will that eventually give you a tree? So our definition is n minus one edges. If we take that definition, right, then why will you get n minus one edges eventually? Is it clear for everyone? That's what we want to show, right? Because we have shown that n minus one is the optimal, n minus one is the minimum. So how do you show that that is what you will get? The process is clear and it seems like it's true, but how do you, and also in a simple way, obviously one can maybe try to use induction and so, but what is the idea? What do you have to explain? So we need to show that you will eventually end up with n minus 1 edges. Okay. But you see, what will you get? What can we certainly say that you will get? So let's just remove this. Okay. What we will get, we end up with a um, we end up with a connected graph. So if I just say it in the most direct way, what we have done, we will end up with a connected graph with no cycle. This is just rephrasing, right? No cycles, or just writing the last step. This is certainly what we will end up with. Right? We will end up with a connected graph which does not have any cycles. Okay. But we have already proved, so I'm basically not proving anything, I'm just quoting something, but I'll explain it also. Okay. We have also proved that a connected graph which does not have any cycles is will have n minus 1 edges. We have proved this. So you can quote that, and that's another definition, right? So one definition is n minus 1 edges. That's the minimum connected graph, that's n minus 1 edges. Right? But uh, for us, the good part is that it can also be looked at as a connected graph, but it doesn't have any cycles. So those two are the same things. But let's just again try to run the explanation. Okay. Well, what we certainly have is this. We have a connected graph with no cycles. This is a minimal connected graph. This is clear. I'm not saying minimum. I'm saying minimal. So minimal connected graph. Now, what does minimal here mean? Minimal means that if you further remove an edge, minimal means that you cannot decrease that particular structure further. What you end up with, what you have is minimal because you cannot further remove something from there. Okay, so in that sense, it's minimal. It's a minimal connected graph, right? Is that okay with everyone? This is what we have. It's minimal because if it doesn't have any cycles, it's very obvious, and we've also seen this in details. It was minimal because obviously if you remove something from there, you end up with a disconnected situation, okay, because of no cycles. And then this is the phenomena that we had stressed upon, that in graphs, or in connectedness rather, I should say, minimal connected graph is same as minimum connected graph. I mean, all minimal connected graph have the same. So this is a, it's not a trivial fact, but we have worked on that, but it's not a trivial fact, right? A minimal connected graph, okay, any minimal connected graph will have n minus one edges. This was the reason why the algorithm worked in the first place, okay? And it's very easy. You can also try to show it if you have not seen this, but yeah, a minimal, any, I should rather say, this is what we have shown. We have spent some time on this, right? And for those who were not, just try to think about this, okay? It's not difficult. A minimal, any minimal connected graph, I mean, this is the reason why the algorithm worked. Any minimal connected graph has n minus 1 edges, okay? Or any maximal graph with no cycles has n minus 1 edges. So it's also maximal with no cycles. If you add another edge, you will end up with a cycle. So those are the same things, and all of them have the same. All of them have n minus 1 edges. Right. And think about the proof if you don't remember it, or just think about it. It's not difficult. You have to basically show that when you start with n points and you try to add edges. So this is same as a maximal graph with no cycles. All right, so you try to add edges so you don't make any cycles, then that algorithm will terminate in exactly n minus 1 steps. Because initially you have n pieces, and when you add an edge, you get n minus 1 pieces, you add another edge, you get n minus 2 pieces, and so you get one piece in n minus, exactly n minus 1 steps, no matter how you do it. So any maximal, so that was the way we proved it, right? Any maximal connected graph, any maximal graph with no cycles has n minus 1 edge. And so that's the same as minimal connected graph, and so yeah, that's what you will get. So there is this chain of arguments which you have to just sit and think, maybe once again, one by one, take example, this example, do it. Okay. Okay. So this is the thing we did. So we are seeing that a consequence of this minimal being minimum, right, that is, or I should rather say, any minimal connected graph having the same size, that is n minus 1. This was the real fact. This was the real thing, right? And a consequence of this is that we can extract a minimum connected graph from any connected graph. And this is very important. Okay, this is sort of the generator for any any connected graph. So it's sort of like any connected graph is built from some minimum. We'll see, and this phenomena we'll see in different places. So given any m edges which connect the thing, you can one by one remove the redundancies and get a minimum connected graph. Okay, and that's because minimal is minimum. So yeah, we will see this phenomena in vectors and vector spaces later on. It is also prevalent in polynomial theory for all the different Lagrange interpolation and different types of basis work. All have similar ideas, but let's not digress ourselves in that right now. Okay. So any questions so far? Right. Now, yeah. No, so if you have, so anyone else would like to explain these steps in your own way, maybe, then I can say it again if needed. Okay, and later on try to phrase it in your own way also, because that's how you should remember it. But anyways, I'll just repeat I've said. So see, it's actually very simple. Okay, but the proof is likely. See, the idea is that we have m edges, we have a lot of edges, and they're making connected graph, and we want to minimize the number of, we want to remove the redundancies. And we know this idea that to remove, this idea is the key thing, is to remove those edges which belong to cycles, because they lead to multiple paths between 2 points. And so you keep removing. So if you do that, then what will you end up with? You will end up with a connected graph, because at each step you're remaining connected. That's the invariant, loop invariant, whatever, if you write a pseudocode. But yeah, and it will not have any cycles. You will end up with a connected graph with no cycles. Okay, but what do you want to show? You want to show that you will end up with n minus 1 edges. You want to show that you will end up with minimum. Okay, but what we have done doesn't a priori mean that it's minimum. It's just we are trying to minimize it, right? Okay, but we end up with a connected graph with no cycles. Now it's a fact, so you can basically, it's a theorem that you can quote, but it depends on what exam it is and so on. So that's why we want to understand it just in all possible ways, so that we just get the idea. Okay, but it's a fact that any connected graph which does not have any cycles will be minimum, will have n minus 1 edges. So that you can use. But if you just try to dig into that, then what is it? Okay, it's a connected graph with no cycles. Okay, I want to show that it is minimum. I want to show it as n minus 1 edges. How do I show that? Okay, what do I know? I know that it is a minimal connected graph. It's minimal, right? For example, this is minimal. Minimal means something that you cannot improve upon. Something, a structure is minimal if you cannot further reduce it, that particular structure. So, for example, this will be minimal. It doesn't have any cycles, means that between any 2 points there is a unique path, and so you cannot afford to remove edges from here. So it's minimal. It doesn't mean it's minimum. It's minimal. Okay, so it's a minimal connected graph. But what we have seen is that, and this was really the idea. This was really the point of this min max, not min max, but all minimal things having the same number of edges. Okay, that was this. Any minimal graph has n minus 1 edges. That's the reason why that algorithm worked. So this will also have n minus 1 edges. Okay, and then that, if you go into the proof of that, then that you should think about once again. It's not hard, but that's something that you should think about. Okay, obviously, and this is also same as a maximal graph with no cycles. So it's maximal means you cannot further expand it. It doesn't mean it's a maximum. Okay, so it's but it does mean in this particular case, but a priori that's not true. Maximal is not maximum. One of the maximals is maximum, but maximal graph or subgraph here, but in any case, maximal graph with no cycles. And all of these have n minus 1 edges, and that's why all the algorithms work. Otherwise, they will not work, because algorithms always find maximals or minimals, because algorithms is locally one step they take at a time and they run, right? So they will always end up with a maximal or a maximal or minimal, something like that. Okay. So that is the thing. Okay, but now this was something that we sort of already knew. There's nothing new I've said so far. Okay, but still, it's just to see that same application of the same idea in slightly different context. But now we want to go one step further. We want to look at the situation in which you have a connected graph. Okay, so we have seen that. So this is again just making a meta point, re-emphasizing the fact that trees are abundant. Okay, trees are abundant. So we saw that starting with endpoints. So maybe this is again something that is we'll quantify it. Okay, we'll quantify it. It's not a thing. Trees are abundant. You see, we saw that starting with endpoints, there are so many ways to get trees, right? You just have to, at each step. So if you take endpoints and you give distributed, just not distribute, but just give n like 100 copies of that to 100 people and ask them to make trees, they'll make it in maybe possibly 100 different ways. If they just want to make interesting trees, they can make 100 different interesting trees very easily, right? Because all you have to do is that each step you have to just ensure that you don't get a cycle. That's all, right? So in that sense, trees are abundant. Okay, but then also it's again getting re-emphasized here in the sense that from any connected graph you can also extract a tree. So they are structurally simple, means from anywhere you can actually just extract one. So they don't have much structural constraints. It's more like they're more like numbers. Okay. And all these are just happening from this phenomena that every maximal is maximum, and maximals you can get in so many different ways because there's like choices at each step, and that's why your trees are abundant. We will also see soon that on n vertices there are n to the power n minus 2 trees. Okay, we will see the details later on, and also many other generalizations of them and so on. So yeah, in any case, let's come to the matter. So we want to take an arbitrary, I'll just use the word weighted here, and I'll explain the phrase weighted connected graph and see how to extract a minimum connected graph. So now, what does weighted mean? First of all, weighted, obviously, as you can understand, it simply means that each of these edges have weights. So now there is discrimination between the edges, and you can find hundreds of problems which reduce to this. You can just, there's so many ways in which can be framed, right? For example, the weight of the edge could be the distance, and if they are cities, and so on, so on. Okay, but for now, let us just put weights and just deal with it. Otherwise, it'll take so much time if we go into the specific problems and so on. In any case, let's actually just take an example. So we have weights. What does it mean? It means that there are some numbers attached. So now we will make a slight change, and we will. So I mean, here you can see that if I put numbers on the vertices and numbers on the edges, it can get slightly confusing. It depends. After some point, it won't be. But what we will do, and this is the convention also, is to use V as the vertices. So we do V1, V2, V3, and so on. So this is just a 6, 7, and then we'll give some numbers on the edges. So you can just give 1, 2, 3, 10, 2. So my example may not be very interesting. Just making it right now 6, 1, 1, something like this. And we are not giving negative weights. Okay, negative weights can be problematic. What happens if there are negative weights? If there are negative weights, then our methods will not work. Then no, 1 minute. I'll think about that. I think certainly no. So yeah. In any case, yeah. Then it becomes a more interesting question. But let's, for the time being, let's just keep positive weights. So all the weights are positive. So let's go slowly. Edges have positive weights. It will also work with negative weights, I think, but for the time being, let's just do this. Yeah, because I'm not 100% sure. Edges have positive weights. You guys can already understand what the question is going to be. So I'm just framing these questions in theoretical sense. These are very common questions, but I'm just phrasing them in the most theoretical way somewhat. And what we want to do is, once again, we want to extract a minimum connected graph. Okay, we want to extract let me just frame it like this: extract a connected graph with minimum total weight. Okay, total weight just means the sum of the weights on the edges of your graph that you have extracted. And also, uh, what just side point, when we said extract a minimum connected graph, we meant extract a tree initially. And so then this tree is basically using all the edges, right? Because it's using all the vertices. So it's also known as a spanning tree, as you can understand, the spanning. But never mind. Yeah. So how do we do this? Well, how do we? So first question here would be, uh, will the number of will the number of edges be fixed? That's the first question. And over the second question is how to do it. Yeah, fixed in the sense, in the so if you are extracting a minimum connected graph from here, okay, then will it have n minus 1 edges? Or should it have n minus 1 edges, or can it have more than n minus 1 edges? If it has to be the minimum, because now there are weights. So if there were no weights, then obviously the weights were all 1, you can imagine, or no weights. Then obviously the minimum was always n minus 1, right? Because the weights are all 1. But now that there are weights, can we say that you will still, the minimum connected graph will still have n minus 1 edges? Yeah. Okay. So, all right. Yeah, you can just take this situation, 8. Oh yeah, if n, yeah. No. N would be the number of, yeah, n would be the number of edges of the whole graph for the cycle. Okay, go on. Sorry. Okay. It's a cycle. Okay. Okay, no problem. Yeah. So let me just let us frame this in a more concrete way. So the question is, will any minimum? So see, will any minimum connected graph have 7 edges in this case, or n minus 1 in general? That is the first question. Let us try to see if that is true or not. Okay. First of all, one must understand that there are several ways to get the minimum connected graph. Right? There's several ways to get the minimum connected graph. That is certainly true, right? Because let's just take a simple example. What if I just make, it doesn't matter, but I'm just taking a simple example, but it can happen in more profound ways. If we take, let's just focus on this example for the time being, okay? If we have this example, then what is a minimum, what is one possible minimum connected graph? And what is a minimum? So in this case, what should it be? Yeah. So in this case, it's quite obvious, right, that you should maybe remove this 3. So you remove v1, v4, right? So you remove this, and then you can remove v3, v4, right? You can remove v3, v4, and you get this graph. It is quite clear that this is the minimum. Okay, I'm not proving it. It's not a proof, But it's quite clear that this is the minimum in terms of the weight also. So that's why I've removed the 3 first. This is the minimum. You can also just do casework and just show that you can't do it because you could not have removed these 5 and 6 cannot be removed. Those edges cannot be removed. So is it clear, number one, that this is a connected graph with minimum weight? Yes, yes. Minimum weight. So it's minimum connected. I well, yeah, that's maybe I should say minimum connected graph with minimum weight is a better word. Yeah, right. Connected graph with oh, that's what I've written here. Yeah, minimum connected graph with minimum weight. That's what I'm talking about. Yes, that's right. And so that yes, that's right, right? Exactly. So the answer is yes. It will always have in mind that's right. That it is in some sense obvious if you see it and spot it. Yes, it's very easy. It will have n minus one edges. Okay. So yes, the answer to this question is yes. But let us just see. Let us first just see that there are several ways to get that connected graph with minimum total weight. For example, this is what we have extracted, right? This is a connected graph with minimum total weight, and the weight is 2 to 4, 5, 10, 16, 18. So the weight is 18. This 18 will not change, obviously. This is the minimum, but there are other ways to do it. So in this case, obviously, we have removed 2 and we have 7 edges. Okay, so n minus 1. You could have done this in a different way, right? But the point is that you would always have, even if you do it in a different way, just to see it in this concrete, you could have removed this and this, but it still has n minus 1 edges. You still have 7 edges. Weight is still 18. And you can see these are the only ways, or maybe there's one more way. You could have removed this, but then you would have to keep this and so on. You see, but you would always, there are many ways to do it, but it will always have n minus 1 edges. That is important. Okay. The minimum is obviously fixed, but it will always have n minus 1 edges. You can't do with less than that. So you can't do with less than that is obvious. Otherwise, it won't even be connected. But if you simply, as we said, if you need more edges than that, then you just suppose you have n edges. If you use n edges, then I'll just remove one of those edges, right? Which so they'll have a it will form a cycle, right? I'll remove one of them from the cycle and I'll have n minus, right? Okay. So if I have more edges than n minus 1, I can further reduce it. That is the reason, simply put. Right? If I have more than n minus 1 edges, I can remove some of them. So obviously, the minimum will always need n minus 1 edges, even in the weighted case. Okay. Please try to make this more rigorous if you need to. Okay. But is the argument clear with the yeah? Okay. This is all. Hmm? Oh, no. So don't go in the negative. Don't go for negative weights. And negative weights, the story will change, right? Yes, yes, yeah. Then it will become more than n minus 1. Then it can become more than n minus 1. Sorry, I didn't get that point. 1 is the minimum weight. that is no. So the weights need not be one. The weights can be just positive numbers. They can be decimals, fractions, right? Yeah, if I've understood your point. Huh? Yeah, so it's a slight. Okay, that's right. But you see, in the negative case, this is not true. Just think about it. It's just not difficult, right? In the negative case, this is not. Mhm. Uh-huh. Yeah, that's what I was thinking, that it will be true there also. That's why I went quite silent in the last one. Yeah. Okay. Let us think about the negative weight situation, since we are, so we are far from the method. Okay, we are just answering some very simple questions right now. But yeah, let me just go into that. I think that is true. Sorry. Yeah. So if there are negative weights, what happens if there are negative weights? Yes, I mean, if there are negative weights, you will still need n minus 1. That is right. Yeah. If there are negative weights. Okay. So the reason why I was thinking that the thing may change, so, was that, well, if there are negative weights, then let's say some minus 2 is there, right? And let's say you make your minimum connected graph, but you do not use this. Without using this, you make your minimum connected graph. Then you may want to add this edge and further reduce the weight. So it seems like you will need more than you should use more than n minus 1. Is that right? But then you get a cycle if you added a negative weight, and then you can further remove another positive weight and get lower even further, right? So you do not, so you will still n minus 1. So using it more than n minus 1 will still give you, will still not give you the minimum, right? Just think about it. But I think Sham has said is a rather more elegant way to say it than what I am saying. He's simply saying, look, even if there are negative weights, just add a large enough positive, just translate the problem, just translate the problem far away from, just so the problem is in some negative coordinate and just translating it in the positive, everything in the positive, just saying that you add a large enough constants to each number, right? Just so that now all the weights are positive. And now to find the minimum for this, right, you will be needing you will be using the same edges, right? A minimum for this will also give a minimum for that, for the original case, by just subtracting 24, 3 into 8, or something like that, 3 into 9, whatever, 9 edges if there are. Okay, so you will still, if there are negative weights, still n minus 1 edges needed. Okay, so I've given two rough ideas, just use them and try to, but again, these are just small bits of exercises which you should do, okay, especially if you have not gotten it in the first. Okay, yeah, but the idea is that you will still need n minus 1. N minus 1 edges will still give you the minimum because we want the minimum. Okay, but is the idea clear? Okay, so let's move to the actual question. So we know that you will still need, so even if there are non-negative weights, you will still need n minus 1. Well, yeah, non-negative weights, so if there are some zero weights, then yeah, then there will be one minimum which will use n minus 1 edges, but there will be other minimums which will not. So if you add an edge with a zero weight, then you can just add it and then you say I have used n edges and got my minimum. But there will be one minimum which will use n minus 1. Those are some simple points you can think about, and not very important. Yes, yes. So okay, I don't know where it went. No, no. So I just said that I think it's lost. Yeah, I just said that if there are negative weights, if there are negative weights, negative weights, still n minus 1 edges will uh, I should rather say still connected graph with minimum weight will use n minus 1 edges. Still connected graph with minimum weight uses n minus 1 edges. Okay, and this is something that you should just think about, and you can let then yeah, just think about this first. This will still use n minus 1 edges. Okay, all right. So let's move on to the actual question. So now but let's just do this problem for positive weights for the time being. And as has been pointed out, you can just add enough numbers and translate this problem to the positive situation. So really, that's the only problem we should be dealing with. But for the time being, let's forget about all that and just do with the positive case. And so we have this. We have this. Yeah. So it will have n minus 1 edges. But how to do it? So sorry, see here there are two things, right? If I ask, does a connected graph with minimum total weight exist? Yes, right? That is very clear. Yeah, existence is clear because you can take all possible all possible connected graph with n minus 1 edges, and one of them will obviously give the minimum. Is that right? Yeah. Mathematically, there is no problem. Mathematically, or rather existentially, there is no problem. There will be one with minimum. Okay. So you take all the trees. There are many trees which you can get from here. Okay. I mean, in this case, you'll get only 3 trees or something like that. But my point is that you can just take the minimum from there. That's easy. But that's not, that doesn't give a rule. Right? That is just an existence. I mean, you have to consider all the cases. There will be a huge number of trees which you can get from a connected graph. If it's the complete graph, if it's all the edges are there initially to start with, then you get into the power n minus 2. So that's impossible to, that doesn't give any algorithm. So the real question is, if this is clear, if existence is clear, yeah, is the existence clear with everyone? Okay. And the real question is get how to get the yeah, how to get it, just how to construct it. That is the actual question. Okay, and even mathematically it implies a lot. I mean, if something exists, but you have just shown that it exists, and but then if you can also find a simple way to construct it, then it also mathematically means a lot of things. Okay, but for the time being, let's, what should be a rule? So we basically want a rule which will work for any tree. Like before this problem, we had a rule, right? You just look at the graph and you just remove the cycles. You just remove uh, one edge from a cycle, and that's very easy to do, right? You list the edges one by one, and you would know which edges are members of cycles. You can you can do it. But what do we do here? Hmm? Yeah, but how do you prove that? So, and really, I should maybe say that, and this is a point which I I also missed, is that, see, in the previous point, what we said is that you look for cycles, right? So in the previous problem, we said look for cycles, remove an edge. You see, this is also not algorithmically very good statement, right? Looking for cycles is not a trivial thing, is it? Right? I mean, if there are n vertices, there can be so many different cycles. If you just say look for cycles, that's also not very good, right? Well, look for cycles and remove an edge is a way to show that there will be, that is a way to show that there will exist a minimum connected graph, or there will exist a tree, right? And rather a little algorithmic, but little constructive way to show it. But it's not an algorithm, right? It's not a very good way to say. What you should actually say, even in the non-weighted case, is to make it slightly easier, is that you start with the points that are given, only the points. Okay, and then the edges are there in a list, right? There is this v, is this blocking, I don't know. So there is v1 v5 v5 v7 and so on. 1 minute. So this is 6. Yeah. This is v6, this is v7 v8, like this. And yeah, so what you should say is that you pick an arbitrary edge that is there in that list. So in the list, the edges will come, right? That is, so v1 v2 is there, and then maybe v2 v3 and v1 v5 and so on, all of coming in the list. So as they come in the list, the v1 v2 comes in, you just add it, and then the next thing comes, you add it. You add it as long as it doesn't form a cycle. If it forms a cycle, then you reject that edge, right? I mean, this is exactly, so exactly what you will get is you will get a graph with no cycles, right? And it will also be connected. So yeah, just you can think about it. It's just the same thing that we did. Okay, but this is the way to run it algorithmically. Yeah, this is the way to run it algorithmically, right? So what you will end up getting is maximal graph with no cycles. Okay, because we have taken all the edges, we have only rejected those which were forming cycles at any stage, and that's all we have done, right? So we'll get a graph which doesn't have any cycles, but it will be maximal among them, right? Because if you take any other edge and add it, you will get a cycle. So that's slightly, it becomes slightly more tricky, but algorithmically, for those who need to actually think about it, there are very rigorous algorithmic proof of this, then you have to think about this also. But mathematically it's the same thing. Just to make it work, it should be like this. That is my point, that to actually say the algorithm, you have to say it like this. So how do you now write an algorithm for the weighted case? Okay, so we can't just say look for a cycle and remove the minimum, remove the edge with the maximum weight, and then how will we show that that will give the min? So roughly it is, so look for cycle, and here, because here it even becomes more non-obvious that this will give the minimum, right? Look for cycles and remove an edge, or look for a cycle, you could say, from that cycle remove an edge with max weight. It's the most obvious thing to do, and this will actually work. But in this, the way in which it is written, it's hard to show from here. Okay, so I mean, in the end, you will get a graph with no cycles, and it will be connected. So non-weightedly, it is a connected graph with minimum number of edges. But how do you show it has that minimum total weight? At each stage we are trying to minimize, so it's a minimal weight, but the minimum thing is not very clear, so one has to think about it. Okay, but if we write this more systematically, and this is where it's interesting, because writing it more algorithmically in a feasible way actually helps you to see a proof also. This works, but this doesn't is not very clear to how to prove it from here, from the way this is written. Look for a cycle and remove an edge and max width. It's a greedy method, because we're just thinking locally. For every time we're trying to minimize, and every opportunity we are getting means when we're finding a cycle, it works, and this will work. But I don't know, I've never been able to prove it. I've never seen a proof of this in this way from here. So see, this is the point of it, right? That even when you're writing proofs, or even for problems which doesn't refer to algorithms, okay, you have to still write thing in an algorithmic way, and that's where it comes in. So how do you write this in an algorithmic way is the question. So this is the task. So you should try to write this in an algorithmic way is the first task, and it's just similar to what we did. Okay, what we did, and that is you start with an empty graph. Okay, I'm not doing the details, but then the proof is the non-trivial part which you guys should think about. Okay, or let me just say a few more things here. Six, seven, yeah. How do you write it algorithmically? You will say, okay, I will take my edges, but I will sort them from smallest to biggest. So first I will take the smallest edge. So algorithmically this will become, I will take an edge. So this was, I don't know what it was, maybe 1. I will take an edge with the smallest weight. So I'll take this edge. Okay, smallest weight. The next edge with the smallest weight comes in. I will see if it makes a cycle or not. If it doesn't make, I will add it. This is also the most obvious algorithm. Even if you write it right, the algorithmic version is also just very obvious to write. So at each stage, the minimum possible edge will come in. So they're coming in an ascending order, obviously. And I will add them as long as they don't make a cycle. This was the algorithmic version previously, but there was no weights previously. So the order was not important. But here it is important. Okay. And this is the form in which we will show that this method will give the minimum. Okay. So the algorithmic version is clear, but to prove it, it's not very clear. Let's just run this completely. Next, this v1, v4 comes in. So because it has weight 2, the 2 is the next one. So we put it. Next, v4, v3 comes in, weight 2, weight 2. Oh, but this is forming an edge. So v2, v3 comes in, it has weight 2, but we don't take it because it forms a cycle. It forms a cycle, so we don't take it. That's the most obvious thing to do. But it's not clear that it works. It's not clear that it will give the minimum weight. Okay, next 3 comes in, we don't take it because it will also form a cycle. It will form a cycle with this one, right? So we don't take it. And that's very easy to check, right? It's very easy for the computer, just if you put an edge, whether it's forming a cycle is very easy. But to find a cycle from a big graph, that's a mess. That's as bad as maybe finding this minimum tree. And then the next edge comes in with weight 5. Okay, I'll put it because not forming a cycle. Next 6 comes in, I put it. And this is exactly what you would get if you follow this method. So you get the same thing. So maybe draw different connected graphs, run both the methods and see that you get the same answer, at least. Check that. So in some sense, you will have an empirical proof that this is true. But the proof, we will try to see it the next time. Okay, and I think next class I will definitely speed it up. We're going a tad bit slow. We're going very slow in some sense, given my goals. Okay, so I will so please work the things out if you need. Okay, this class is slightly maybe advanced for some people, but just work it out. It's an interesting thing. Work out the details. Okay, and if you need, you can just review the videos. I upload it so that now we'll try to go faster, because today I wanted to do that network problem about frequencies and such, the minimum number of frequencies needed, or classroom allocation. I wanted to do that. I wanted to see this in coloring, greedy method in the coloring of graphs, which is a good thing too. And then I wanted to count the number of trees. Then I wanted to something about balancing trees, but it's only one. So we'll go a little fast next time. Okay, so just be prepared, and so you can enjoy it. Okay, think about the matters we have done.